AP Cacus BC, Unit 5, Day 9, office hours. So these problems were out of your old book from last year, Calc AB. The author's Anton, one of the authors. So 25 I want to point out. So you should have checked your odds in the back. Most of these are odds, at least half of them. 25 kind of is an interesting result that I think I might disagree with. So we'll check it out when we see it. Let's try these problems. So problem number 1 says, in each part determine whether the integral is improper, and if so, explain why. So you're not being asked to actually find the answers. You're just being asked to identify if there's an issue and what is the issue. So this one right here, what I noticed right away is that x cannot be 3, which creates a vertical asymptote, which is an issue for this guy. So I'm going to say that it is improper. And the reason is that it has an interior infinite discontinuity at x equals 3. So that's my answer. It is improper. This is why. Interior infinite discontinuity, where? So B is 1 to 5 of dx over x plus 3. So x cannot equal negative 3, which is okay for us. It's not an issue. And we shouldn't have any issue. This is a proper integral. So this is not improper. But you could show your work, like I have, in identifying what the issues potentially would be. C, 0 to 1 of natural log of x dx. Well, you guys know what the natural log graph looks like. It has a vertical asymptote at x equals 0. So x cannot be 0. Oh, wait. I guess the directions specifically said, yeah. So, x cannot be 0. It can't be negative. It has to be positive, and so we're dealing with the value. So this is going to be improper. It has an endpoint infinite discontinuity. Endpoint, not interior. Interior would be between the limits. This is the actual limit itself at x equals 0. So that's what we're looking for. D, there's a lot of these. Negative 1 to positive infinity, e to the negative x dx. So this, right away, this is improper because you're integrating to infinity. So we have, they say, in the book, they say interval limit of infinity. Some about the limit being infinity. E is negative infinity, positive infinity, dx over the cube root of x minus 1. So x cannot equal 1 is an issue. And you're integrating to infinity. So you should name all those things. Improper, because it has an interior infinite discontinuity at x equals 1. And interval limits of negative infinity and positive infinity. This has pretty much everything you could ask for in an improper integral. So that's E. I'm going to squeeze f right here because it's the last one. F is 0 to pi over 4 of tangent Now remember, tangent is sine over cosine, right? So whenever cosine equals 0, that's bad, which happens at pi over 2 plus pi k, so negative pi over 2, so forth. But that's not an issue for us, right? So I think we're all good. Not improper. Now, if it went to pi over 2, that would be an issue. That'd be a problem. So just quickly kind of getting you good at identifying these things. Problem 2 says in each part determine all the values, and we're just doing part A, for which all values of p force integrals improper. So 0 to 1 of dx over x to the p. So the issue here is going to be if this equals 0, right? So what values of p are going to cause division by 0? Oh, any value p. Well, if it's a negative value, it actually ends up on the top, and that's not an issue. If it's 0, that's fine, right? So p can equal 0, p can be negative, p cannot be positive. So all values of p less than 0 are when that integral is improper. All right, let's see, number 4. Number 4 is negative 1 to infinity, x over 1 plus x squared dx. So this is improper right there. Now, there is no division by 0, so we're fine with that. We're going to need to integrate this. U substitution, not inverse tangent. U substitution works great. That x dx done with the 2. So it's going to be 1/2 d over u. So that's going to be 1/2 natural log of the absolute value of u. So that's going to be 1/2 natural log of the absolute value of 1 plus x squared, which we don't need absolute values anymore. The limits are going to be, well, it's going to be limit as b goes to infinity of negative 1 to b. So let's plug limits in. One half natural log of 1 plus b squared minus 1/2 natural log. If you plug negative 1 in, it's going to be 2. So as b goes to infinity, this goes to infinity, and this whole thing goes to infinity. The thing blows up. It goes to positive infinity. It diverges is the technical answer on the AP test. Technical answer is diverges. Or divergent. Okay. Number 5. 4 to positive infinity of 2 over x squared minus 1. Now, you might think, oh, this is going to be inverse tangent. Nope, if it was plus, it would be. Now, you might want to figure out where we have issues that x cannot be negative 1 or 1, which is not an issue for us. But we are going to infinity, and we do need to use partial fractions. So a over x plus 1, b over x minus 1 dx, multiply through by the least common denominator. You guys should be getting good at this. Plug a negative 1 in if you want. A equals negative 1. You can plug a positive 1 in. B equals positive 1. So this is going to be equal to the limit as b goes to infinity of 4 to b of negative 1 over x plus 1 plus 1 over x plus 1 dx. So we're going to integrate. Limit as b goes to infinity of negative natural log the absolute value of x plus 1 plus natural log the absolute value of x plus 1 4 to b. Probably combine those together. Limit as b goes to infinity of natural log the absolute value of x plus 1 over, I messed up something, let me see. It's supposed to be minus there. X minus 1 over x plus 1. So if we plug b in, we get natural log of absolute value b minus 1 over b plus 1 minus natural log of, plug 4 in, you're going to get 3 over 5, 3/5. Okay, as b goes infinity, this gives you infinity over infinity, which then gives you 1, and natural log 1 is 0. So the final answer is negative natural log of 3/5, or you could write it positive natural log of 5/3, bring the negative in as an exponent. But it converges. So, all right. Let's see, number 10. Number 10, negative infinity to 2 dx over x squared plus 4. This is going to be inverse tangent. We got to take a 4 out of everything in the bottom, though, because this needs to be a 1. So if we do that, get x squared over 4. And then what we plug in here, that's going to be your u. So x over 2. So u equals x over 2, du equals 1/2 dx. Don't want the 1/2, multiplied by the 2. So we rewrite this as, we have a 1/4 in front already, and now a 2. And it's going to be du over u squared plus 1, which is going to be inverse tangent of u. And so now, it's going to be inverse tangent of x over 2. Limits are b to 2. So inverse tangent of 1 minus inverse tangent of b over 2. So what's inverse tangent 1? What do you plug into tangent to get 1? Well, that's sine over cosine, principal values. What angle does sine and cosine give the same thing? That's going to be pi over 4. Right? What happens to inverse tangent as you go to infinity? Now, we've sketched this graph a couple times lately, so maybe you actually remember it, but it looks like this. It's the tangent graph sideways, and it has these horizontal asymptotes at negative pi over 2 and pi over 2. As you go to infinity, you're going to pi over 2. So these common denominator could be 4. So that's going to be, and we already have this 1/2 in front. So that's going to be pi over 4 minus 2 over 8 is going to be negative pi over 4, negative pi over 8. But I feel like I made a mistake. I think I'm getting close. Oh. We're going to negative infinity. So we're actually going to negative pi over 2. So as it becomes a plus, it's 3 pi over 4, 3 pi over 8, positive 3 pi over 8. There we go. Watch out for those little mistakes. Okay, 11. Negative infinity to 0 of e to 3x dx. No potential infinite discontinuities. There's no vertical asymptotes. So, but we are integrating negative infinity, so obviously that's an issue. So let's see. It's going to equal the limit as b goes to negative infinity. B to 0, e to the 3x dx. And so we're going to integrate. It's going to be e to the 3x with a 1/3. So it's going to be 1/3 e to the 0 minus 1/3 e to the 3b. Now that's going to be a 1. That's going to be 1/3. Now as b goes to negative infinity, that's the same thing as 1/3e to the infinity. So this can go to 0. So the answer is just going to be 1/3. It converges. All right. 17. 3 to 4 dx over x minus 3 squared. So are there any issues? Well, x cannot be 3. Ooh, that's an issue. So we have a vertical infinite discontinuity on the end. So we're going to have to approach this with a limit as a one-side limit. We're going to approach 3 from the right side. This is between 3 and 4. So you got to go from 3 to 4. So it's the right side of 3 to 4. B to 4. This is going to be a power rule. So that's going to be x minus 3 negative 1 over negative 1. I'm going to rewrite it. Negative 1 over x minus 3. So we're going to plug the limits in. Plug 4 in. That. B in. Now, as b gets close to 3 on the right, that's like 3 plus there. It's going to be going to 0, but positive 0, right? So that's going to go to positive infinity. And the negative 1 just doesn't even matter. So it's going to go to positive infinity. And it diverges. Diverges. Okay. 19. 0 to pi over 2. Tangent x dx. So tangent, sine over cosine. So whenever cosine 0, you get vertical asymptotes. And that happens at pi over 2. So, and it happens again in other places, but specifically for what we're concerned about, pi over 2. Yeah, we also have to integrate this. It's not secant squared. You should probably think it was like sine over cosine and do u substitution. U equals cosine x. Du equals negative sine x dx. I don't want the negative. So this is going to be the limit as b approaches pi over 2 from the left-hand side. And this is going to be negative du over u. So that's going to be negative natural log of the absolute value. And so it's going to be negative natural log of b minus negative natural log of 0. Oh, 0 is an issue too. Shoot. Right? No. 0 shouldn't be an issue. But oh shoot, I forgot to put the cosine back in. cosine of b cosine of 0. So yeah, natural log 0 is an issue, but cosine of 0 is 1. So, which is going to be 0. This is, as you approach pi over 2 from the left for cosine of b, it is approaching a value of 0. And it's, just imagine what the cosine curve looks like. So we're approaching pi over 2 from the left-hand side. So it's going to be positive, which is fine. An absolute value is positive, but natural log, as you approach 0 of natural log, it goes to negative infinity. There's already negative, so it's going to go to positive infinity. Diverges. That was kind of interesting. Okay. Now 25 has something interesting going on, so I might try a couple different ways, but 25 0.3 of dx over x minus 2, so x cannot equal 2, which is a vertical infinite discontinuity right in the middle, so we got to break it up. We got to say limit as b approaches 2 from the left, 0 to b. And then we have to do limit as b approaches 2 from the right, b to 3. So that's the way we set it up. And so then we get limit as b approaches 2 negative. This is going to be natural log of the absolute value of x minus 2. Just going through the motions. That's going to be natural log of 2. It's going to be natural log of 1. That's going to be 0. Okay, what happens as we approach 2 from the left-hand side? It's going to be like 1.999, so it's going to be negative small quantity. But you are taking the absolute values. But this is going to go to negative infinity. So we just look at the graph. What happens is you get closer and closer to natural log 0. It blows up. Minus natural log 2. Plus here, this is approach 2 from the right side, so it's going to be a very small positive quantity. But it's going to go to negative infinity. Right? And there's already a negative in front of it. So now, do these cancel each other out? You know, we studied these before. We'd say this is an indeterminate form and we need to do, Lopsided Rule or something. I mean, do these cancel out? It's hard to say. I mean, I think they are coming from the same size terms, but that's not like a great support for it. What I could say, so this is kind of interesting. You could do Lopsided Rule. Let's see. Now, I think the back of the book has this as divergent, but I don't think it is. I'm going to show you in a second. So if we were to do Lopsided Rule, it would be this would be natural log of something tiny over something tiny, right? This one has a minus, so it ends up in the bottom. And so that'd be Lopsided Rule. And this is, b minus 2 over b minus 2. It's natural log of 1. This would end up being natural log of 1, which is 0. And your final answer would be negative natural log of 2 or natural log of 1/2. So I think the back of the book says divergent, but I think this is the actual answer. The other way to think about it is to look at the graph of this. So the graph of this has a vertical asymptote at x equals 2. horizontal asymptote y equals 0. And we're trying to integrate it from 0 to 3. And the graph looks like this. Now, 0 to 3. Okay, now isn't this shape of this graph right here the same as this one? Don't they just cancel each other out and then you're left with this? So 25 is converges, but it takes a bit of analysis to get that. So negative natural log 2 or natural log 1/2. All right, a couple more problems, 28 and 31. 28 is 0 to 4 of dx over x minus 2 to the 2/3. So x cannot equal 2. So we're going to split this up. This is the interior infinite discontinuity. So we've got to break it up into one-side limits, two different ones. So this is going to be limit as b approaches 2 from the left, 0 to b, plus the limit as b approaches 2 from the right side of b to 4. So this is power rule. X minus 2 to the 1/3 divided by the new exponent 3. Same antiderivative for the other one, so don't overthink it. All right, plug in the limits. All right, so we have the limits plugged in. Okay, what happens? As b approaches 2 from the left, so that'd be like 1.999, this is going to be a negative tiny quantity. So the third power is 0, right? And then over here, you plug in 2 from the right side, so that's like 2.0001. It's going to approach 0 positive, but a positive one. But cube root of that times 3, well, that's nothing. That goes to 0. So what's left is this right here, positive 3 cube root of 2 plus another 3 cube root of 2. So 6 cube root of 2 converges. All right, 31, last one. 0 to positive infinity, e to the negative square root of x over square root of x dx. So how are we going to integrate this? I mean, x equals 0 is an issue, right? So looks like we got to do one side limit there, and we go to infinity. So there's two issues here, right? We have an infinite discontinuity on the end, and then we have a limit of infinity also to deal with. So we got two issues. I think we could try use substitution as if it were what's inside, because the derivative of this is going to be 1/2 x and negative 1/2 dx, which is 1/2 times 1 over the square root of x dx. That's perfect. Don't want the 1/2 though, right? Okay, good. So this is e to the u du, e to the negative u, right? So, okay, so it's going to be negative e to the negative u. So this is going to be the limit. Oh, this is kind of hard. I feel like there's two limits involved. We got two things. I don't know. I haven't done this before. Say as A approaches 0 from the right side and B approaches positive infinity of negative e to the negative square root of x, A to B. I don't know. It's like a double limit. All right. I don't know. I'm making this up. Good. I mean, we can maybe somehow figure out how to write in both terms of both of them, but it's going to be negative 1 over e to the negative square root of b minus, no, we already took care of that, minus negative 1 over e to the square root of a. So as a goes to 0, this is going to get closer and closer to 1, right? E to 0 is 1, so that's going to be 1. This is going to blow up, so that's going to go to 0. So I think the answer is going to be, now I'm saying that the answer is, oh shoot, I forgot about the 2. 2, 2, 2, the answer is 2. It converges. There we go. These are tough. You gotta watch out those details. All right.